Okay, let's dive right into the solution. I called the base p of x and the exponent q of x, so it will shorten the notation. So in case 1, this becomes 1 if p of x is just an element of R without 0, and q of x is equal to 0. Since if an exponent is 0 and the base is just a real number, the result will be exactly 1. So we just have to solve that x cubed minus 5x squared minus 2x plus 24 is equal to 0. And since this is a monic cubic, which means this coefficient is 1, we know that all the roots should divide this last term, which is 24. So all the possible roots are in plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 8, and plus or minus 12. And that are all the possible options. Now, to test some of these roots, we will use Horner's method. So I can quickly see that 1 and minus 1 are not roots of this polynomial, but we can see that minus 2 is a root if we fill it in, since this gives minus 8, minus 20, which is minus 28, plus 4, plus 24, which gives minus 28 plus 28, which is 0. And Horner's method works like this. We draw two lines, we put the root in here, minus 2, and here we will write all the coefficients of our polynomial, which in this case is 1x cubed minus 5x squared minus 2x and plus 24. And now we apply Horner's method. So we slide the 1 right here. 1 times minus 2 is equal to minus 2. And then we add minus 5 and minus 2 to get minus 7. Then we multiply minus 7 times minus 2, which gives 14. And we add minus 2 and 14 to get 12. 12 times minus 2, minus 24. And 24 plus minus 24 is equal to 0. And that's great, because that means that our remainder is equal to 0. And we are left with this polynomial of degree 2. So what we learned is that we can write this cubic as x plus 2 times x squared minus 7x plus 12 is equal to 0. And now let's use a quadratic formula to factor this even further. So, of this thing, the discriminant is equal to b squared minus 4ac. So that gives us minus 7 squared minus 4 times 12 times 1, which is 49 minus 48, which is 1. So x1 is equal to minus b, which is 7, plus the root of 1, which is 1 over 2, and x2 is equal to 7 minus 1 over 2. So that is 8 over 2, which is 4, and 3. So we can factor this into x plus 2 times the coefficient of the highest power, which is just 1, times x minus the first root, 4, times x minus the second root, which is 3. So we get that x is equal to minus 2, or x is equal to 4, or x is equal to 3. But now we have to check that the base evaluated at these 3 values isn't equal to 0. So let's check that. So p of minus 2 is equal to minus 2 cubed minus 2 times minus 2 cubed minus minus 2 plus 1, which is minus 8 plus 16, which is 8, plus 2, which is 10, which gives 11. So that's okay. Now p of 4 is 4 cubed minus 2 times 4 squared minus 4 plus 1, which is 64 minus 32, which is 32, minus 4, which is 28, which gives us 29. So that's also great. And p of 3 is equal to 3 cubed minus 2 times 3 squared minus 3 plus 1, which is 27, minus 18, which is 9, which gives 6, which gives 7. So we get our first set of solutions, which I will call V1, and that is the set minus 2, 3, and 4. Now let's go to case 2. Now case 2, when is an exponential equal to 1? Well, if just the base is equal to 1 and the exponent is a real number. So let's write that down. P of x is equal to 1 and Q of x can be anything. But if it is 0, then we will have solutions in common with the first set of solutions. So this happens when x cubed minus 2x squared minus x plus 1 is equal to 1. Since then, we will get 1 to the power of something, which will always be 1, of course. So let's solve this. This is equivalent to x, and I will factor an x out, times x squared minus 2x minus 1 is equal to 0. I move this 1 to this side and then factor out a factor of x. And then this is just a quadratic, so we can calculate the discriminant, which is b squared minus 4ac, which will be minus 4. So we get the discriminant of 8. So x1 is equal to minus b, which is 2, plus the root of 8 over 2a, which is 2. And x2 is minus b minus the root of 8 over 2. So this gives that x1 is equal to 1 plus, and this we can write as 2 root 2. So this becomes root 2, and x2 is equal to 1 minus the root of 2. So we can factorize the polynomial in x minus the first root, which is 1 minus root 2, times x minus the second root, which gives 1 plus root 2. So this is equivalent to x times x minus 1 minus root 2 times x minus 1 plus root 2 is equal to 0. And this is 0 if all the linear terms are equal to 0. So we get that x is equal to 0, or x is equal to 1 plus root 2, or x is equal to 1 minus the root of 2. So we found 3 new distinct solutions to our equation. So v2 is equal to 0, 1 plus root 2, and 1 minus root 2. And now we are ready to go to case 3. Now, if you forgot one case, I think you forgot case 3, which happens if p of x is equal to minus 1 and q of x is an even integer, so into z. So an even integer. Since minus 1 to the qn is equal to 1 for all n in z. So let's solve this last case. So this means that x cubed minus 2x squared minus x plus 1 is equal to minus 1. So if we move the minus 1 to this side, we get x cubed minus 2x squared minus x plus 2 is equal to 0. And now we will use Holness method again. So all the possible roots should lie in the set plus or minus 1, and since that are the only roots of 2 in z. So let's test 1, and we get 1 minus 2, which is minus 1, minus 1, which is minus 2, so then we get 0. So 1 is a root. So let's use Holness method again. We write the root here, which is 1, and then we write all the coefficients above, which is 1x cubed minus 2x squared minus 1x and plus 2. So we slide the 1 down, times 1 is equal to 1, minus 2 plus 1 is minus 1, minus 1 times 1 is minus 1, minus 1 plus minus 1 is minus 2, and if we multiply this we get minus 2, and the result is 0, which is what we want. So by this method we know that we can write this polynomial as x minus 1, which is the root, times what's left over, which is x squared, 1x squared, minus 1x, and minus 2. And now this is easy to factor since I can see that minus 1 gives 0 in this factor. So this is just x minus 1 times x plus 1 times, I have to obtain minus 2, so this is x minus 2. And both of them have to be 0. And if you factor this out, you can see that this equals this one. So the solutions are x is equal to 1, x is equal to minus 1, or x is equal to 2. So we get v3 3, minus 1, 1, and 2. So what is now the collection of all solutions of this mysterious equation? It is the set minus 2, 3, 4, 0, 1 plus root 2, 1 minus root 2, 1 minus 1, and 2. So we got 9 different solutions. And if you like this problem, don't forget to like and subscribe.